Hey everybody, this is Larry. This is day 2 of the October Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Gonna be here all month. Hope y'all are having a good time. And today's problem is combination sum. Okay. Distinct candidates and target list of all unique combinations where the chosen sum is the target. Okay, the same number may be used an unlimited amount of times. So that's the difference, or that's like something to take a note on. Two combinations are unique if the frequency of them are different. Okay. So in general, this is going to be dynamic programming. Yeah. And I'm just thinking about, so usually I would do this bottoms up. I'm going to try to do it top down today to kind of illustrate how to do it top down. And then again, I have a video that goes into the thought process about going from top down to bottoms up, and then to the space optimization technique. But so for now, I'm going to do it top up or top down. And the key thing to note is that and all you have to do is, in this case, that means that you can apply for a given number any number of times. And from that, we have a target. So what is the recurrence here, right? The recurrence here, then it's going to be, okay, let's just say we have something called get count. And one thing that I would remember is just the index, because, and the remaining, right? And I'll explain this in a bit. So index is equal to the index of the suffix of candidates that we have to consider. Because we only, so one thing to notice is that for dynamic programming or memorization, we use the optimal subproblem. And in this case, once we're done using a number, we want to structure it in a way such that once we finish using a number, we don't have to go back to it. So that's why that this suffix thing works. And then the remaining is maybe a little bit more obvious. It's just the remaining number we have to get to. Is it greater than or just exactly? Seems like it's exact, because sometimes it's some indication of that. Yeah. And then now this is if remaining is equal to 0. We have to check that. Okay, I was just double checking that each candidate could be 0, because if it's 0, then it makes some math a little bit trickier. But otherwise, if it's 0 to 0, we could return 1. If remaining is less than 0, that's actually, yeah, then we return 0. And then otherwise, that means remaining is positive. If index is equal to n, then we may also return 0. And we set n is equal to the number of candidates. Cool. And then now we just have to kind of figure it out, right? So what is the transition here, right? Well, we just want to sum up the counts of return get count of. So there are two ways to kind of go about this, right? Is given a candidate, we either use it or we don't. So we can just break them out, right? So use candidate count. So the number of count if we use the candidate is, well, we're still in the same index because we may want to use it multiple times, right? So it's this index and then remaining minus candidates of index, and then we use or don't use candidate count, and once we don't use a number, we're done, right? Because we don't want to go back to it. And in this case, it makes sense because in this case, the order doesn't matter. So that, you know, if going 2 3 2 is just counts once, the same as 2 2 3. So in this case, you can do it that way. And one more thing to kind of talk about while I'm typing this is that one thing to know is that this can be done with memorization and dynamic programming by noticing this is a directed asynchronous graph. There's no cycle in this implicit graph, because either remaining goes down or index goes up, but so that there's no like loop thing, right? So you don't have to worry about that. And then at the very end, all we have to do is just sum up use candidate count plus don't use candidate count, and that should be the answer. And to kick it off, we return get count of the index starting from 0, and then remaining is just the target, right? So this is not going to run too fast, but it's just, just to see if it works, right? Oh, I might have messed this up a little bit. I thought you have to return the count, but instead you have to return the thing. So, that's a little bit weirder because I thought that it could go up to... I thought the complexity may be a little bit trickier, but still, no worries. We could still solve this. I just misread the problem. But let's kind of print this out then we could use this debugging to kind of prove our exponential exhaustive search or something like that, depending on how it goes, right? So yeah, so it returns 2. There are 2 answers, and that matches our thing here. Let's put in the other ones real quick. We need a test case montage here would be good, but yeah. Totally misread that one though. Whoopsie daisies. But if nothing else, we should probably get what we expect. Okay, so this looks good in that it matches the count of what we expect. I think one thing that allows us to kind of go, and I guess in this case it doesn't really matter, it's basically a big number, right? I think that was the thing that I thought may be a little bit weird, but maybe I don't. Sometimes Leetcode also has just like terrible test cases, so I wasn't sure. Because I thought this could be exponential in a weird way. Yeah, this is already judging too slow, right? Okay. Yeah, this is actually time limit exceeded because, as I expected, it shouldn't be possible. I mean, okay, let's even just do like 100, right? Even 100 is too slow because this turns out to be like a variation of the Fibonacci with the 10 numbers, and you could kind of prove this a little bit. Yeah, wow, this is that's what. So what I'm doing right now is kind of why I didn't think. I was wrong about the Fibonacci, but it's probably like the stirring numbers or something like that. But But yeah, but the reason, oh, this is only 16. Okay, maybe I was wrong. Because I was just gonna do an LRU. I was gonna convert this to a memorization, and for fun, I'm just gonna go memorize it just to kind of see what that would give me. Because this is actually a common-ish dynamic program problem. So 51. Oh, so that's not actually that bad. I thought it would be more exponential. Let's try that. Yeah, so even this simple one has 6,000 entries, right? So if you're gonna think about max case, so that's actually, now that I think about it, I don't really like this problem, and that's actually why that's why I gravitated to the dynamic programming problem, because there is an actual solution. The reason why I didn't read this correctly is because, as you can tell, given these constraints, and I only did it up to 10, so you could, probably change it up to 30 and it'll be bigger. But given these constraints with only n is equal to 10 and 500, we see that there are about, what is that? That's more than 2 trillion responses, right? So So this is in that regards, this is a crappy problem because it relies on you to assume that the problem is going to be to give you like these constraints are not good constraints in that it assumes that you trust that the constraints are good enough. But that's why I did it this way, right? Because there are over 2 trillion responses for something that's is not even the max case. So how do you solve this knowing that this is not dynamic programming? And because this gets a little bit meta, and the meta part is that one, you know that this is going to be solvable, and two, from that you know that there's only one way, which is that you have to do something that is output sensitive, meaning that because you have to return the results, the best that you can do will have to be output sensitive, right? Meaning that if you need to return 2 trillion array elements, it's gonna take at least 2 trillion time, right? Like there's no easy way to be better than that. So in that case, in that kind of meta, thinking about this problem, this becomes, I think, essentially a backtracking problem, and then you just have to do the best you can. And the backtracking way is the same way that we've done it just now. In a way, I mean, there's a little bit more state keeping, but we'll just do it with backtracking. So let's just do return results. I don't know how that happened. And then return results, and then now we just have backtracking, right? And there are a couple of ways to backtrack, and we have the same, index and target. But for us to keep track of because now that we need to know the output, we have to keep track of the previous states as well. So let's just keep track. Let's just say prefix or something like that. And then now again. Maybe I shouldn't have deleted the code, but that's fine. If index is equal to n, if target is equal to 0, we do something like results.append prefix. And this allocates actually a new array for those of you who might be curious why I do it this way. Otherwise, you're going to keep on appending the same reference, and that's no good. This should return, of course. And then if index is equal to n, also return, because that means that we've used all the numbers, right? Oops. Whew, okay. So then now we backtrack. This is the same actually, and maybe this is a good exercise to kind of see the similarity between backtracking and top-down memorization. And in this case, we can see that there are only two cases, right? Which is use candidate. Right, so use index here, so which is we backtrack. I guess I don't know why I did backtracking instead of backtrack, but in either case, so prefix plus the number. So this is the prefix appends the number, which is candidates of index, and then target minus candidates of index, and then the other one is backtracking with just the prefix. And then index plus 1 and then target, right? And in usually backtracking, depending on how you implement it, and this is implementation detail, you have to push a change and then roll back that change. Generally speaking, in this case, we allocate a new variable for it. Essentially, is what we did here, so we don't have to roll back the change, same as here. But if you had like a for loop or something, then maybe you have to do it that way. And then now to kick it off again, this is very similar to our dynamic programming. And if you watch this video backwards, you might even be able to if you watch this video backwards, you may get from how you do from backtracking to dynamic or top-down dynamic programming. So it's kind of amusing that way. I had to take this out because this is just not going to run, but we could take a look at the other ones real quick. Yeah, so this looks good so far. I think we had one more. Where is this? But let's do it for 20 or something. Much smaller number. Yeah, this looks maybe good. I mean, I don't know. This looks good enough. I can't tell I'm not going to count every thingy, right? So cool. So let's submit it, give it a go, see if it's fast enough. If it gives me a TLE, I'll be a little bit sad, but it's accepted because otherwise, this is as fast as you can go because we go as fast as we can. Yeah. So basically, a breakdown here. What is the complex of backtracking? It's always a little bit tricky to say. In this case, it's going to be a function of the target and the index. It's going to be output sensitive, and in a way, it's all of it's tricky to say. It's going to be exponential, as you kind of saw with just 30 or with 10 numbers and 500. It was already 2 trillion. So yeah, it's suffice to say that it's an exponential class. In terms of space, it is output sensitive. So you can't really do better than that. It's optimal. Yeah. That's all for this problem. I hope you can maybe even watch this video backwards if you want to upsolve a little bit to do the dynamic programming way without the reconstruction of the array. Let me know what you think. Let me know how you solve this problem. I will see y'all tomorrow. Bye bye.